Everyone. I would just like to say hello and welcome to tonight's event. Thanks for taking some time on a Monday evening to learn a little bit about physics and James Bond. Once again, if you all feel comfortable, feel free to put on your videos. We would love for this to be casual and personable. We think that would be great. Special thanks to the University Alliance Ruhr and to Professor Tolan for organizing this and for coming up with the idea. The German Center for Research and Innovation exists to promote German-American scientific exchange and to foster transatlantic networks and focus on questions of the future. So that's topics like physics, but it's also topics like artificial intelligence, cities and climate change, or this year we're going to be looking at the society and transition effects of the pandemic. So special thanks to all of you for showing up and participating in this transatlantic exchange that we're all about. We're hoping to have fun tonight looking at Hollywood and physics, what is real, what is artifice, and it's a little bit out of our wheelhouse to have an event on this kind of topic, but we're really excited. So I will pass it over to Peter Rosenbaum, who is the Executive Director of the University Alliance Ruhr New York office.
Thank you so much, Jared. Thank you, Julia. Welcome, everyone. Hollywood, physics, this is what we are all about. The University Alliance Ruhr. My name is Peter Rosenbaum, or I should say Rosenbaum, Peter Rosenbaum, of the University Alliance Ruhr office here in New York. And I want to welcome all of you, particularly our speakers, Metin Tolan, who's joining us from Germany, so it's very late for him. It's around midnight, and Hannah Kaufman, who's joining us from New York. Our conversation tonight is about Metin Tolan's book and his video presentation, Shaken Not Stirred, James Bond in the Spotlight of Physics. The video premiered on YouTube this past Friday and is available for all of you to watch on the YouTube channel of Universitätsallianz Ruhr. And Long, if you could just post a link in our chat box, that would be great. You find the link on our website as well. And just this morning, by the way, we uploaded what we call the Director's Cut, an updated version of Professor Tolan's presentation that was produced at TU Dortmund University's very own television studio and its teaching channel that has been on air since 2009. Without further ado, let me introduce you to our speakers. It's a great pleasure for me to welcome Metin Tolan. Metin Tolan is professor of physics at TU Dortmund University, where he has been the chair of experimental physics since 2001. He received his PhD from the University of Kiel, where he also finished his postdoc. His main areas of interest are the use of X-rays to study the interface behavior of polymers, biomaterials, liquids, and other soft materials, and the use of synchrotron radiation in materials research. With more than 200 refereed journal articles and book publications, Metin Tolan is not only an internationally recognized expert in experimental physics, but he's also a true science advocate who, in his books and numerous lectures, explains phenomena and puzzles from everyday life, history, and film through the lens of physics. His books on the physics of soccer, the Titanic, Star Trek, and James Bond make the world of physics accessible to a larger audience, including those of us who, like myself, were relieved to just get a passing grade in physics back in high school. It's no surprise that Metin Tolan was the winner of the 2013 Communicator Award, an award that the German Research Foundation and Germany's Donors Association for the Promotion of Sciences and Humanities present annually to researchers who make their work and research accessible to a wider audience in innovative, diverse, and effective ways, and who engage in a dialogue between the research community and the public, something that we particularly need these days. Welcome, Professor Tolan. Our second speaker and moderator, Hannah Kaufman, is an associate editor at Springer Nature, a global scientific publisher. Part of the Springer Books team, Hannah manages a large program of academic and general interest titles, primarily within the fields of astronomy and space science. Based in New York, Hannah is here today representing the popular science portfolio to which Professor Tolan's book and the overarching science and fiction series belong. Welcome, Hannah. So the way we're going to do this is Hannah and Metin are going to have a conversation for about half an hour, and you, the audience member, have the opportunity, as Julia explained, to pose questions, comments using your chat function. And after the conversation, feel free to raise your hand using the commands at the bottom of your screen. And if we don't get to address all of your questions, simply send them to us, to me, via email at office@uaruhr.org. I will post that email address in our chat box in a minute, and I'll be happy to forward your questions to our speakers. So without further ado, Hannah, I'm turning it over to you. Thank you all for coming.
Yeah, thank you, everybody. Thank you, Peter, and thank you to the University Alliance for having me. This is a really fun and special event, so I'm really glad to be a part of it. And yes, I'm here on behalf of Springer and, representing from the editorial side, the books that we publish, and Metin is one of our authors, so it's really great that we get to be here with him and see how he's interacting with the community and share some of this research with you. So with that, I do want to jump into my first question for Metin and maybe take us back to the beginning and when you were first researching this book. What made you decide to start studying the physics of James Bond movies?
Well, I can clearly remember the first time I was thinking about physics in the James Bond movie was in the year 1995. So 26 years ago, when the movie GoldenEye was coming to the cinemas. I was sitting in the cinema and looking at one of the first scenes in the movie where James Bond is after an airplane and he jumps from a cliff after an airplane, and he was able to catch the airplane and to get out of the difficult situation with this stunt. And so, of course, everybody was laughing because, well, it looked a little bit, interesting, I would say. But I was immediately thinking, could this be true, at least in principle? At least in principle, when you calculate it, could it be possible to catch the airplane in the air? And if yes, what is under which circumstances is this possible? I tried to calculate it in my head during the movie, which was not successful because it's quite complicated to do this. But when I was at home, I immediately switched my computer on. At that time, it was an Atari computer. Probably some of you know what an Atari computer is. And I wrote a program to solve all the mathematics. And after a couple of hours at night, I was really able to bring James Bond in the airplane. And so this was a great fun. And then I was just thinking, well, if I am going to teach sometime physics, this would be a great example for the students to recalculate this. And then 6 years later, this happened. I came here to Dortmund at the chair Experimental Physics 1, and I had to teach undergraduate students, and I took this example. And the students had really a lot of fun in calculating this. And so I was thinking, well, for the next topic in the lecture, there could be another James Bond stunt to check. And this was the stunt from the man with the golden gun, the spiral jump of the car over the river, which you could see in the movie if you have already seen the movie. And I did all the calculations. The calculations are not that difficult, I have to say. Of course, the makers of the movie, they are saying, well, everything has to be calculated very accurately and it is tremendously difficult. This is definitely not the case. I would say undergraduate physicists can calculate this. In fact, when I'm giving now the lecture physics for undergraduates, this is an exercise in homework for the students to calculate the stunt. So you can see it's not that difficult for a physicist. And I did the calculation, and of course, this was again a great fun. And then I found other examples. And then 1 year later, for a popular lecture here at the university, I was asked to give a lecture, and I took all the calculations out and give a popular lecture about this. Well, and then the things developed. There were people sitting in the audience, and they asked me, couldn't you give this talk at my company, for instance, to entertain our customers? And this was the start of this. And then in the year 2005, somebody from my German publisher Pieper were coming to the university asking me if I want to write a book about this. And in 2005, I told him I do not have the time for doing this. And but he insisted. He was saying, well, just do it. There is no such book available on the market. Please do it. And in the year 2007, I told him, well, I can do it under two conditions. Number one, I need a colleague to do this with me, my colleague from the theory department, Joachim Stolze. And number two, I would like to do this with students. So we organized a seminar with students, and the students looked at all the different scenes, at very small clips from the different movies, and they did the calculations, and they figured also out very interesting things. And in the year 2008, this book was published in German by Pieper just before the movie Quantum of Solace was coming to the cinemas. So this was the start of the idea. And then I think Pieper had the rights for the book, of course. And I think in the last year, they were negotiating with Springer. And this was a little bit difficult. I have not understood why, because I was not interested. But finally, it was successful. And this book came out, the English version. I have to say, in the meantime, there was a version in Portuguese. This has already been published. I have to say, the Portuguese version is, at least from the images, it is really nicer than the German one. I did not tell this my German publisher, but again, the English version is nicer than the German version, I have to say. So, and even nicer than the Portuguese version. This was also interesting because I told Springer that I do not have the time for the translation. And then Mrs. LaHaye told me, well, we only need a rough translation. We do the fine translation we do with a native speaker. And then I did the most of the translation with the translation program DeepL, which is, I did not know this before. I told Mrs. LaHaye this never work. This can never work. I doubt that this can work, but it did work. I could put basically the German text, including all the figures with the complete format in this program, and it took the program 2 minutes to produce a version 0, 2 minutes for 250 pages. And I just had to make some corrections. It took me 1 day, and then it was brushed up by a native speaker from Springer. This was, of course, very astonishing. Of course, the translation was not perfect by this DeepL program, but I was really astonished that it worked in this way. And so we also, what is also interesting is in the English version are much fewer mistakes than in the German version. Because this was another iteration. So this is not only the most recent version, but it is also the most correct version of our book, which is available on the market.
Well, I may be biased, but I definitely recommend the book, you know. Yeah. So, yeah, Metin, I mean, the fact that it was translated also into Portuguese, you know, this seems to be just a concept that a lot of just lay readers, I think, can relate to, just bringing physics to the everyday level. And I was interested to know, you know, you've been following this concept for a while now. You know, you got interested in it in 1995. So I wanted to know, you know, you take a look at different Bond movies. And have you seen any changes or trends in the way that science and physics have been portrayed from, you know, a film like GoldenEye up to the present day?
Yes, unfortunately, the science is really becoming less important in the movies with Daniel Craig, because you can see that these movies are, well, action movies. James Bond movie is becoming more and more a normal action movie. And in these movies where the action is dominating, of course, physics is not dominating so much, because when you have a car chase and two cars are crashing, well, a physicist can also not say too much to this. And all the fine, small details with a nice stunt, which was really calculated by physicists. I mean, it has to be calculated by physicists, otherwise it's not working. This is not done anymore, because with the realistic animations, you can produce things which are just not possible. And for physicists, the movies are not that interesting anymore. But I must say, I'm a James Bond fan. I really like the movies with Daniel Craig. So, so physics is just the second issue in the movies for me. There are also some Daniel Craig scenes which are now in this book, because in the original German version there were hardly any scenes with Daniel Craig, but here now are more. But of course, in the old movies, there are very small, very little scenes. For instance, you can see a mirror image of an attacker in the eye of James Bond in the movie GoldenEye, not GoldenEye, Goldfinger, just at the beginning. There is a mirror image of an attacker who attacks James Bond, and he sees a mirror image of the attacker in the eye of the lady he is going to kiss. And from this scene, you can, for instance, calculate the size of the attacker. You can calculate that all this does not really fit. And at the end, you can calculate that the curvature of the eye of the lady has to have a certain value, which means at the end that the lady cannot see anything. The lady is basically blind. This is what you can calculate. So these small things are not present anymore in the real action movies with Daniel Craig. But this is James Bond. It's not a physics lecture, it's James Bond. But you can see the same trend in another favorite of mine, in Star Trek, for instance. In Star Trek, in the Star Trek episodes of the 1990s of these years, with Next Generation, Captain Picard, and Voyager, Captain Janeway, for instance, or Deep Space Nine, you can find a lot of physics. In the new episodes with Star Trek Discovery, there is hardly any physics in these episodes. They are perfect space adventures, I have to say, really perfect. The making is great, but there is almost no physics which you can discuss as a physicist. So it's the same trend that movies are becoming more and more, or going more and more, well, in the direction that they become pure action movies rather than having fine scientific elements in them.
Okay, and we do actually have a question already in the chat, and this refers back to the presentation that you gave and that people could watch over the weekend. So it's by Todd Schwartz, and he asks, in the video you explain that the spiral motion of the car has no impact on the length of the jump. If that's the case, why then is throwing an American football in a perfect spiral so important to the quarterback?
Well, what is the question? The spiral motion. You're saying the motion around the axis of the car, not the speed of the car. The speed of the car has, of course, an impact on the length of the jump.
He's
But you
referring to the
say
spiral motion.
the spiral. Well, this is just because the energy in the spiral is much smaller than the energy in the jump. So this is only true because the spiral is just, the car just makes one spiral around the axis. I did also the calculation for the case if the car would make two spirals, two rotations or three rotations, then of course the rotations are much more important for the jump itself. But for the stunt, as you can see it in the movie, where the car is just one time rotating around the longitudinal axis, there it is really, it has no impact on the length of the jump. This is just because the spiral is so slow and it is just one spiral. But in principle, you're right, it should have an impact on the length of the jump, but only if the rotation is faster than in this stunt. This is, by the way, this is also what our students are calculating when they do the calculation.
And then could you remind us or clarify again for that stunt that you showed in the presentation of the car doing the flip between the two ramps that were kind of askew, were there special effects involved with that? Was there an actual driver who rode that car over the ramps?
Yeah. Well, this was a real stunt, of course, because at that time the computers were not that developed. It was in the year 1974. So the computers of the year 1974, well, they could not perform this photorealistic animations as they can do at the times nowadays. But they did it with a real stuntman, and they did the calculation, the exact calculation. But the trick was that the car was perfectly balanced. It was perfectly balanced. They had to prepare the car. They had to cut the car in the middle. They had to put the steering wheel exactly in the middle. The stuntman was lying exactly in the middle, fixed by belts, and with such a prepared car, so that it was a perfectly balanced car with respect to the longitudinal axis. Then it worked already at the first try. It was working. And this spiral jump was just in the beginning of the 70s. It was a stunt which was shown in stadiums for an audience. People were just doing it in order to entertain people. And then the makers of the James Bond movie, they just bought this stunt. They just bought the stunt. They were saying, we want this stunt for our movie, and we buy it, and you are not allowed to show this stunt for a couple of years because they want to have it in an exclusive manner. There is even a patent. There was even a patent on this stunt. So you can see, you can do a lot with physics.
Yeah, that's very interesting. And I wondered also if you wanted to explain again sort of why you named the book Shaken Not Stirred and how cocktails and martinis and such have to do with physics.
Well, I named it Shaken Not Stirred because I think this is the most famous quote of James Bond. He is drinking his vodka martini shaken, not stirred, as we all know. I have to say that I do not know from my own experience why he is doing it, because I'm not drinking any alcohol. So I cannot say from my own experience why he's doing it. I have thought about a fun explanation which I gave in the book, and I can tell you the fun explanation and the real explanation. My fun explanation is when you take a very close look to a vodka martini through a microscope, when you even look down to the molecules, then you find that a vodka martini is a mixture of small and large molecules. The large molecules are responsible for the taste, and the small molecules, its alcohol is a small and very compact molecule. This is, of course, responsible, I would say, for the bang. These are two molecules, and the big ones are responsible for the taste, and the smaller ones are responsible, well, for the alcohol, or for what alcohol is doing, or for the fun, you can say. And now one just has to know that there is in the field of granular matter, this is a subtopic of physics, when you shake a mixture of large and small particles, then for some magic reason, the large particles are going to the top. You may have seen this when you have a mixture in the morning, when you eat in the morning. What is the English word for muesli, Mr. Rosenbaum? What is
cereal? When
okay.
you eat morning cereal.
Yeah, when you eat this, it's a mixture of small and large particles, and then you very often, when you open the box, you can see that the big parts, like the nuts or the raisins, are on the top, and the smaller parts are on the bottom. This is called the Brazil hazelnut effect. This is the physics term of this. The Brazil hazelnut effect means that the bigger parts are going to the top. Well, and then my theory is, when James Bond is shaking his vodka martini, the bigger parts are going to the top. The bigger parts are responsible for the taste. And so he has never the time to drink the full vodka martini. He can at most drink one mouthful, because he has no time. He has to go to his next adventure. And my theory is that he really likes the taste of this vodka martini, and he is shaking the taste to the top, so that he can drink one mouthful of it with the maximum of the taste. This is my theory. In reality, there is a flaw in the argumentation, because in physics you have diffusion. And if this really is true for a liquid, you can think about this by yourself. The real reason is much more boring. James Bond is drinking his vodka martini with ice, but the ice is being taken away by a net when the vodka martini is shaken with ice, and then there is a net, and the vodka martini is put to the glass, for instance. So by shaking the vodka martini, the liquid is just in closer contact with the ice rather than by stirring it. This means the shaked vodka martini is colder than the stirred vodka martini. And this is a true reason. Bartenders have told me this. But this is a very boring reason with not too much physics involved. And this is the reason why I just mentioned this in a footnote in this book.
Thank you. And then we do have another question that came in, again by Todd. This is switching gears quite a lot. I don't know if you'll be able to answer this on the spot. It's a two-part question based on the film Diamonds Are Forever. Could you build a diamond-based laser, put it on a satellite, and destroy targets on the ground? And the second part is, how would they get the diamonds back to Earth?
Well, first of all, diamonds have nothing to do with a laser. This is unfortunately a flaw in the movie. The argumentation that diamonds have to do something with a laser is not correct. The first laser was built with a crystal made of aluminum oxide. This was a basic material with some impurities and not with diamonds. So unfortunately, this is not true. With the diamonds, you may use diamonds to focus a laser beam. This could be possible, but this is truly the most expensive way to focus a laser beam. It is much more simple with an ordinary lens or a mirror or whatever. You do not have to use diamonds for this. So I cannot really explain why they are using diamonds there. Installing a laser in an orbit around the Earth, which can really destroy rockets or a submarine under 100 meters of water. We calculated, of course, also the power you need for this laser, and the power, unfortunately, is much larger, or fortunately, is much larger than all you can really realize at the moment. You may know in the US that you had a president in the 80s who made a program out of this. He wanted to construct lasers in space in order to destroy rockets from enemies. This was in the 80s, well, I would say much beyond what was possible. Nowadays, one has to say, with lasers, of course, you can melt metal. You can even produce lasers with really very strong lasers with very strong power. And you can even penetrate through thick metal plates over a distance. This is possible. But what you do not can is what you see in the movie Diamonds Are Forever, that the rockets are really that they disappear, that they are vaporized, or that a submarine which is underwater is also vaporized, because with the laser beam you also have to vaporize all the water which is on top of the submarine. You can just calculate the energy which you need, and this is far beyond the energy which you can really create with all of the lasers in the world. But there is a project in the US which is called the National Ignition Facility in California. There you have the strongest lasers on Earth, but the size of them is well, they have the size of a large building, and with these lasers one is trying to do the fusion of hydrogen atoms in order to generate energy, as it is done in the sun. But with these lasers, you cannot really use them as a weapon, because they have only very short pulses with which you could destroy probably one rocket. But then you have to wait for, I would say, days in order to switch the laser on again. So this laser would also not be possible to do it. But one has to admit, yes, we have now strong lasers. Yes, they can penetrate metal, but no, not in the way as you can see it in the movie Diamonds Are Forever. And I cannot tell you why they use diamonds, because it sounds great. It sounds great, I must say. bringing these diamonds back would not be too difficult, because taking satellites in an Earth orbit and bringing them back has been done with the space shuttles for a long time. This is not too unusual these days.
Yeah, and going off of this note, your book was published in our science and fiction series, and to an extent, James Bond is kind of science fiction-y, the way that the gadgets are portrayed. So I was wondering, beyond diamonds and lasers, were there other technologies that were based off of cutting-edge theories or ideas at the time that later came true or did not? And, in the older movies, how much of that has come to fruition now?
Well, James Bond is always using technology where we would say it is at least possible that it really works. So, for instance, in the movie Die Another Day, he has an invisible car, which is, of course, you cannot, at the moment, you cannot buy an invisible car, but still we have materials, metamaterials, they are called, with which you can make, or with which you can cloak objects, so that you cannot see it with particular electromagnetic waves. This is possible, not with light, but such cloaking devices are available for wavelengths which have already slightly longer wavelengths than light. Light is an electromagnetic wave with a rather short wavelength, but with longer wavelengths, you can already cloak objects. Not as perfect as in the movie, but I think it will not take too long to cloak an object as we see it in this James Bond movie, for instance. So this is not out of the physical theories of the experiments physicists are doing, and probably this will be possible not with this perfection, but this will be possible in a couple of years for whatever reason. Well, if you cloak things, probably for not so positive reasons, but it doesn't matter. And of course, you also could see in the movie You Only Live Twice. He is flying a very small helicopter, which is really a helicopter where he is just sitting in the helicopter, and it's a very small device. This small device was also working. It was really working, not as perfect as you could see it in the movie, but it was just constructed. And this is also a perfect example for a technology which was shown in the James Bond movie and which became later on very common. There is in the movie Thunderball. At the beginning of this movie, he has a jetpack, which is he was just flying with a backpack. He is just flying out of a difficult situation, and this was just operating because the U.S. Army has invented it. At that time, of course, they wanted to use it in the Vietnam War. But nowadays, such a flying backpack is at least possible, and you can fly also a couple of minutes with this. At the time of the James Bond movie, you could only fly a couple of seconds with it. So this has also been developed for whatever reason. It will never be something which we can use because the fuel is a little bit too expensive. So it is an interesting development. It has been used in a James Bond movie, and it has been further developed by scientists to make it more and more perfect.
Thank you. And then we do have two questions that rolled in. The first is from Sarah Beth Lardy. It's about the car stunts. So many of the car stunts seem to rely on physics working out perfectly, jumping a gap in the road, spitting out to evade a chasing car, etc. Are these things that a secret agent could be taught to calculate so quickly?
Yeah, also first of all, I have to say, James Bond obviously is able to calculate these things very quickly, because in the movie GoldenEye, in the scene which I mentioned at the beginning, it is absolutely clear that he can solve coupled nonlinear differential equations just with his brain. And I can tell you, coupled nonlinear differential equations are one of the most difficult things a physicist can think about. So he is obviously able to calculate this in his brain. I had to use a computer when I did it. So this is the proof that a secret agent is very good in physics. This is a definite proof, because otherwise James Bond would already be dead. And also for other car chases, for instance, in the movie Diamonds Are Forever, he is turning his car around on two wheels and then driving through a very narrow gap. And putting a car on two wheels, you have to make it in the way that you are driving always little curves in order to balance two forces, the gravitation and the centrifugal force. And so driving in this not straight, but in a way where you make left and right turns in a very fast way, you have to also calculate a little bit the diameter of the circular movement you are going to do. So obviously James Bond is also able to do this. So a stuntman at least has to have a feeling for this, what is going to happen. A stuntman does not have to be a physicist. I have spoken to stuntmen because they asked me if I can give a lecture at their place, and these were the German stuntmen group, which was located in Cologne. They asked me for a talk, and they told me, well, they were not able to calculate it, but they had the right feeling. They had the right feeling for the stunts. So this was a very interesting talk which I gave there, and it was also really interesting to hear what they were thinking when they are doing such a stunt.
Interesting, thank you. It's very interesting to think that they just feel it a bit more intuitively, and then to learn the science afterwards for how they actually have pulled it off.
They told me, for instance, the stunt in Diamonds Are Forever, when you put a car on two wheels, they told me this is very simple. This has to do, each beginner stuntman has to do this. If you're not able to do this, you can immediately go away.
Wow.
Well, they are saying it is similar to riding a bicycle. And in fact, when you look at the physics, it is exactly the same. So if you're able to ride a bicycle, you can do the stunt, which in fact, when you try it, I don't think that I can do the stunt, but I can ride a bicycle. So, but this is what they were saying.
Yeah, well, I pray for them that that was not the mindset for the spiral jump scene of the car, and a little more planning went into that.
Yes.
So we do have another question from Ben Caldwell. He says, one of my favorite foreshadowing technologies was the satellite tracking in James's car in Goldfinger, in which he tracks a homing device. This obviously foretold GPS tracking. How feasible was this at the time?
At this time, it was completely not feasible, because for a GPS tracking, you need satellites in the orbit of the Earth. And in fact, having a GPS which is working around the whole world, you need at least a number of 20 or even more satellites which are orbiting around the world. The theory of GPS was already available. The physics and the theory, because the interesting point of GPS is that you have to know Albert Einstein's general and special relativity so that GPS is working. If you do not know the general and special relativity, your GPS would not be as accurate as it is. You would lose the accuracy of a couple of kilometers per day. And the reason is you have to have a very accurate time in your satellite because you are measuring the time a signal takes from your car, for instance, to the satellite. And so when your time is not accurate, then your GPS is not accurate. And there are very tiny deviations in the time of the satellite with respect to the time on Earth due to Albert Einstein's relativity theory, special and general relativity. And only if you take these time differences into account, then you get an accurate GPS system as we have it now with an accuracy of a couple of meters. If you don't have this, the accuracy of GPS would be a couple of kilometers, which makes GPS essentially useless. And so this was developed. The theory of general and special relativity was developed in the years 1905 and 1916. Yes, but it was not possible at that time to bring so accurate clocks in an orbit in the Earth. Number one, atomic clocks were just on the horizon. One was constructing the first ones, but they were really large and they could not be transferred to an orbit. And this is the most important reason why it was not possible to even come close to GPS. But the principle of GPS was there in the year 1964. This was the year of the movie Goldfinger. So in principle, one could have constructed it, but not in reality because atomic clocks were too large at that time. And of course, it was not so common as it is today to put a satellite in an orbit. Of course, this was also a little bit more difficult at that time.
Yeah, interesting. It would be very interesting for a modern audience to take a look back at that movie and not even blink twice at a scene like that. You know, it's so commonplace for us.
Yeah, but it is true that this was a sort of a forecast because physicists at that time, they have known that this could be possible, from the physics point of view. For instance, but it's also funny when you think about it the other way around. If Albert Einstein would not have discovered the special and the general theory of relativity, then an engineer could try to develop a GPS system. And the engineer would have worked hard and harder and harder and harder, and he will never be successful because he can only construct a GPS system with an accuracy of a few kilometers per day. And he was thinking about, well, probably I have not constructed it in a correct way. He would try to look for a mistake, but the mistake is that the physics was not fully understood at that moment. So, and it's also interesting that something like the general and special theory of relativity, which seems to be completely useless for us, it has a tremendous impact because all of the GPS systems rely on this theory.
Okay, so we've got 2 questions left with about 8 minutes to go. So the first is from Peter, And he asks, as far as technology is concerned, which would you consider to be the most creative James Bond movie?
Oh, well, the most creative James Bond movie is, in fact, Goldfinger. It is clearly Goldfinger. You have to know that, and this is a very interesting story. In Goldfinger, in the movie Goldfinger, Goldfinger uses a laser and he threatens James Bond with a laser. The movie is from the year 1964 and the laser has been invented in the year 1960, 4 years before. And when the laser has been invented, people were thinking, this is a solution, but we do not know the problem at the moment. This is what people were saying. But after the movie Goldfinger, everybody knew what a laser is and what you possibly can do with such a laser beam. So it has really popularized, the invention of the laser became really popular after the movie Goldfinger. And a very interesting side story is, in the book Goldfinger of Ian Fleming, the creator of James Bond, the book was written in the year 1959, 1 year before the invention of the laser. And in the book, there is, of course, not a laser, but a rotating saw, which is also interesting and nice, but the laser is, of course, much nicer. So, so this is really an interesting technology asset in this movie. In this book, there is an own chapter for the movie Goldfinger, because you have a lot of physics or fun physics facts of Goldfinger. For instance, why is the lady dying because of their gold paint? I mean, she has been painted with some gold color, and but why is he dying? Why is she dying? And you can calculate this. You should not really paint your skin for a too long time, because the paint prevents you from sweating, and this prevents you from losing heat due to sweating. So the heat which you are producing is going inside your body and heats you up, and then if you have it too long on your skin, then your temperature is rising and you are dying when your temperature is rising to 42 degrees centigrade. And so, so this is also the mechanism why the lady is really dying. She is dying because of their own heat. For instance, you are creating a heat on average of 100 watts. This is what a human is creating. So if you invite somebody to your home, you can tune your heating a little bit down, because the person is bringing 100 watts with him. And when you cannot radiate the heat into the room, but you radiate the heat inside your body, then your body is going to heat up, and one can calculate, if you do this for 6 hours, then you die. And obviously this lady was hit, and so she probably was not dead, but obviously she was not awake for 6 hours, and then she was dying. This is the mechanism. And you find a lot of these things in the movie Goldfinger. So you find really a lot of physics in the movie Goldfinger. And as I'm saying, in the old movie, probably the older a movie, the more physics you can find in the movie.
And with that, we are approaching the end of the hour. So I want to hand this back off, I think, to Peter so he can close us out. And thank you again, Metin. This has been really lovely.
You're welcome.
Thank you guys so very much. Thank you, Hannah. Thank you, Metin. So I guess the takeaway lesson is don't paint yourself all over your body, right? Resist the urge. Don't do it. I feel that we should have a whole series of James Bond movies, watch one James Bond movie at a time and have Metin explain to us what's going on, what's possible, what's not possible, and drink lots of shaken martinis. We will do that once we can gather. In the meantime, thank you so very much for being with us tonight. That was fun, and there's nothing nicer than being in a diehard fan club of, you know, James Bond folks. So thank you for joining us. And if you have any questions, reach out to us. I'm going to leave my address here, office@uhr.org. Have a wonderful evening. Stay safe, and I hope to see you soon. All right. Thank you.
Thank you.
Thank you. Thank you, Metin. Thank you, Hannah. Thanks.
Thank you.